Hello everyone, this is my presentation for the mathematical modeling project. So as you can see from the image, the topic that I chose is the Rubik's Cube. Most specifically, the math behind the 3x3 Rubik's Cube puzzle. So the focus that I chose to give this project is the mathematical model that allows us to represent the movements of the Rubik's Cube using a mix of permutations and group theory. So by movements of the Rubik's Cube, I mean the turning of layers around an axis. So the axis is inside the cube, that is rather from the mechanism. But those are the legal moves in cubing, only the turning of faces. So using this model, we want to predict how the cube is going to change after a certain sequence of moves. Most specifically, OLL and PLL algorithms. So in cubing, we have these algorithms. There are basically sequences of steps that you need to follow of the turning of the faces so that you can reach a solved cube state. So OLL stands for orientation of the last layer. Basically what you want to do is all of the yellows facing up. And once you have that, as in this case, then PLL, it rearranges the pieces into their place. So we want to see the corner pieces as one piece rather than three stickers, but one piece. So you want this piece to go in this way and this piece to go in this way, and well, this green edge piece would need to go here and this orange edge piece would need to go here. So that's what PLL does. It puts all of the last layers, that's why it's permutation of the last layer, it puts all of the pieces of the last layer in its place without changing their orientation. Okay, so because before that, before OLL and PLL, you can reach this state rather intuitively, so that's why it is focused on OLL and PLL only. And with this model, also understand why some states of the cube are unsolvable. What I mean by unsolvable is that imagine that you twist this corner. So if you want to go to the fully solved cube state, which means all of the blue stickers facing one side, all of the yellow stickers facing one side, all of the red stickers facing another side, and so on and so forth. So if you want to reach that state, but you twist a corner, then you can no longer reach a solved state using only legal moves. Remember that a legal move is only the turning of layers. So we want to explain why that happens, why you cannot reach a solved state if you twisted, for example, a corner, or if the cube popped, which means basically it exploded and you reassembled it. What's the chance of being able to reach a solved state again? Now, in order to understand this objective, we need some math on permutations and group theory. So we need to remember that permutations are ordered arrangement of objects. So, for example, we could name the top four corners of the cube. So the one containing yellow, red, and green, 1, yellow, orange, and blue 2, yellow, green, and orange 3, and yellow, red, and blue 4. So if we perform a turning of that layer, then we would reach another state. So that's why we need permutations. Also, composition of permutations, which means to, okay, so now that we have this permutation, then what happens after you perform another permutation and another permutation, so that we eventually reach an algorithm either from OLL or PLL. And group theory, because if we group all of the possible moves in the Rubik's Cube, we can form a mathematical group, and we need to remember what a group is. So a group is a set of elements that they are held together by a specific rule, and their fundamental properties do not change. So we need to fulfill, for it to be a group, we need to fulfill some properties like closure. So it means that if you combine two elements that are within the set, then the result is also within the set. Associativity, identity element, inverse element, so all of them are present in the Rubik's Cube. And finally, a commutator is the equation that I decided to explain this time. So basically, a commutator, what it does is it rearranges some pieces without affecting most of the cube. Okay, so the faces are going to be labeled as such: F for front, R for right, U for up, L for left, B for back, and D for down. So if it is a clockwise move, it is going to be like such, but if it is a counterclockwise move, then it is going to be it is going to have an apostrophe. So F, F prime, R, R prime, and so on and so forth. So this equation is called the commutator. It depends on two moves. It could be either F and R or R and U, whichever. And what it does is that it first performs a move, then a second move, and then its inverse. So the counterclockwise rotation of that move. So in this sense, we rearrange some pieces. Why is this important? Because we rearrange some pieces, but we do not scramble the whole cube. So that is the idea behind the commutator. That's why we want it, because in OLL and PLL, we want to change some pieces of place, but not by affecting the whole cube. So that's why it's used. It's useful. And that would be it. Thank you.